Okay, this is exam 1 for physics 102 in spring 20. Consider this arrangement of charges. Draw the electric field vectors acting at point A. Oh, and actually, I'll change this, but you're also supposed to find the magnitude and direction of those original vectors. So let's just draw them right here. I have E1 is going to be up and towards that 75 nanocoulomb, and then E2 is going to be in this direction. So E1 and then E2, and then let's go ahead and find the magnitude of E1. That's going to be kq over r squared, that's 9 times 10 to the ninth, times q, which is 75 times 10 to the minus 9 coulombs, divided by the distance. This distance, let's see, it is a 3, 4, 5 triangle, is 5 meters. That's squared. So this cancels with that and leaves 3. 75 divided by 25, and then these cancel, and that leaves me 27 newtons per coulomb. And then I can do a similar thing for E2. Divided by this distance right here, which is 3. Gives me 9 newtons per coulomb. So that's the magnitudes of E1 and E2, but then I also need to know this angle. To find that angle, you can say the inverse tan of 4 over 3, which is equal to, what's that, 53 degrees. You didn't have to do the inverse tan if you just said 53 degrees, that's fine. Okay, so that was for part A, and then calculate the x and y components of the electric field vectors. I'm going to draw a figure here. I like to draw figures. So E2 is 9 newtons per coulomb in this direction. And then the x and y components of E1 are 27 sine of 53. And then over here, 27 cosine of 53. This is equal to 22. And this is equal to 16. And then to find the, let's see, that would have been okay for that. You have to go to really the next step as well. So I'm going to go ahead and do that. I have one component over here that's 16 minus 9, that's 7 newtons per coulomb, and then I have 22 newtons per coulomb. All right, so those are my final vectors, and now for part C and D, this would be, if you didn't have that second, if you didn't do this part right here, I wouldn't have counted off, but you have to do it to get part C and D, so that has to happen. So for part C and D, I have to find the magnitude. I'm going to redraw this up here. I have a 7 Newton per coulomb vector here and a 22 Newton per coulomb. And so the resultant vector is right there, and it has a magnitude equal to 7 squared plus 22 squared. That's equal to 23. And then the direction is this angle, I'll call it phi, is inverse tan of 22 over 7. And that's 72 degrees above the negative x-axis. So that is part C and D. And then if you place a charge at point A of 2 coulombs, what is the direction and magnitude of the force experiences? All right, so for part E, I know that F is equal to Q times E. So I'm putting a charge right here where I know the electric field is 23 newtons per coulomb, and so that 2 coulomb charge will feel a 46 Newton force. And the direction of that is going to be the same, 72 degrees above the negative x-axis, and it's only the same because it's a positive charge. If it was a negative charge, it would be exactly the opposite. So that's above the negative x, it would be below the positive x if it were negative, but it's not as positive. So that's the answer. All right, draw the field lines. The important thing here is that I get twice as number of field lines as I have coming out of the 20 coulomb are as going into the minus 10 coulomb as I have coming out of the 20 coulomb. And so it should look something like this. Or like I could have 3 field lines coming out there, but then I would need 3, 4, 5. Is that right? Yeah, I'd have 6. Did I have 6 there? 1, 2, 3, 4, 5, 6. Yeah, that's right. Um, Hold on. Sorry, did I mess that up? Yeah, I don't have that field line. So that's sort of the bare minimum. Or if you wanted to draw more, you could. Like if I drew a field line right there, then I would have to draw another field line right here. But like I said, this is fine. I have 2 field lines going into the minus 10 and 4 coming out of the plus 20, and it should follow sort of that general look. Consider this configuration of charges. What is the magnitude and direction of Q2, or the net force on Q2? Let's just draw those forces. I'm going to have one force in that direction. I have another in this direction. I know it's going to be smaller. In fact, it's going to be 1/4 the size of the left-leaning vector because it's further away and it's the same charge. Let's calculate each individual force. So I'll do F21. It's going to be 9 times 10 to the 9th times 1 times 10 to the minus 4 times 4 times 10 to the minus 5 divided by the distance squared, which is 1 meter squared. Notice that these all cancel out. I'm just left with 36 newtons. And then in a similar way, what's that, F23. But look, I know it has to be 9, right? Because it has to be 1/4 of that original force because it's twice as far away. But let's just go ahead and show that. 9 times 10 to the 9th, 4 times 10 to the minus 5, 1 times 10 to the minus 4, divided by the distance squared, which is 2 squared. That cancels out there, and there, leaving me with 9 newtons. So those are my 2 forces, giving me a net force of 36 minus 9 equals to 27 newtons. So my sum of all my forces is equal to 36. Actually, it would be 9 minus 36 is equal to minus 27 newtons, or you could say 27 newtons to the left. Either would be correct. If Q2 has a mass of 2 kilograms, what is its acceleration? All right, well, this is harkening back to last semester. F equals ma. A is equal to F divided by m. That is 27 newtons divided by 2 kilograms. That's 14 meters per second squared. Obviously, those numbers are not very realistic when we're talking about these charged particles, but they're just sort of for an exercise. All right, let's look at the multiple choice. Which of these vectors best represent the force on Q? Okay, so I have a small charge here, but a short distance away, and then a bigger charge that's twice the distance away. So I'm going to have, say, this force due to that charge, and then, remember, F, K, Q, Q over R squared. I've doubled the charge, but I've doubled the distance, so that means that I've halved the force. So it means D is the right answer for the net force because I have a big vector, I have a smaller vector, and so my resultant vector is going to fall below that 45-degree line. Here shows 2 cubes, 1 and 2, that are attracted to each other. If they're attracted, they have to be opposite charges, say plus and minus like that. Then cube number 3 is a neutral conductor. Which of these scenarios will occur? Well, if cube 3 is a neutral conductor, that means that it's going to be attracted to both of them. So C is the right answer, remember, because you'll get this. If this is positive, then you're going to get negative charges over here and positive charges over here. And if this is negative, then you're going to get positive charges and negative. You'll get an induced charge in that neutral conductor. Two charges experience an electric force of 12 newtons. If you double the distance, what's the new force? F equals kqq over r squared. I'm keeping the charge is the same, but I'm doubling the distance, so I'm quartering that. It was 12 newtons divided by 4 is equal to 3. Proton and electron initially separated, released from rest, which will experience the greater magnitude of acceleration. They both experience the same force, plus, minus. They feel a force that's attractive, that's equal but opposite, but because the electron has a mass that's about 1/10,000th that of the proton, it will feel a much greater acceleration. Oh, look, this was from the quiz, but y'all liked it so much I decided to bring it back. So here, remember, I can draw my vectors for my force vectors. Here, if that's 2 units long, this will also be 2 units long. That means that this is going to be 3 units long. This will also be 3 units long. This is going to be 6 units long, and also 6 units long. So I have 6, 6, 3, 3, 2, 2. And so the answer, of course, is 3q. I expect you, hopefully, all of you got that one right. What is the magnitude of the force on the plus 4 nanocoulomb charge? All right, so I want to know the magnitude of the force on this charge is going to be down in this direction. F is equal to kqq over r squared. That's 9 times 10 to the 9th. 4 times 10 to the minus 9. 2 times 10 to the minus 9. Divided by this distance. Oh goodness, it's the square root of 2 squared plus 2 squared equals the square root of 8. I'm just going to leave it as square root of 8. You'll see why. Because if I square that, it just becomes 8. And I can do some cancellations. There, 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 and there. And I'm left with 9 times 10 to the minus 9 newtons. Oh, B is the right answer. What is the direction of the force? Oh, look, I already drew the vector, so I know it's because this is an equilateral right triangle. This is 45 degrees. You try it. Tan minus 1 of 2 over 2. That's equal to 45 degrees, or you can just recognize that that's an equilateral right triangle, and so both of these angles are 45 degrees. This is 90 degrees. So it's 45 degrees below the negative x-axis. Let's see. B is right there. It's not C. That's not. These are sort of in the wrong quadrant. That's the wrong angle. 135 from the positive x-axis. That would be over here. That's 135 degrees. That's not right. So yeah, B is the right answer. Q1 has a magnitude of 10 coulombs. It's going to be plus 10. Then Q2 I know has to be negative. Oops. Q2 has to be negative, so that gets rid of that. Okay, so I still have 4 options. I also know that Q2 has to be less than 10. Oh, that doesn't help me. So I really got to do some work here. 1, 2, 3, 4, 5, 6, 7 lines. So I have 10 divided by 7 is 1.4. That means that each line has a worth of like 1.4 coulombs. And so 3 times 1.4 is equal to actually this is 1.43. That's equal to 4.3 coulombs. All right, and I know it needs to be negative, so C is the right answer. The electric field is mostly directly related to, remember, electric field is force per charge. So it is most directly related to the force acting on a test charge. Positive charge is brought near to a neutral conductor. What happens? I'm going to get negatives over here, positives over here. B is the right answer. What's the electric field at this point? Okay, so the big mistake would be to use the 5 coulomb charge. This is meant to be an easy problem, but I suspect that it's not going to be deemed easy. I know I have an electric field down and in that direction. Not because I have a plus 5 coulomb charge there, but because I put my imaginary test charge there, and that's the direction of the force that that imaginary test charge feels. Both of these will have a magnitude of 9 times 10 to the 9th, 10 times 10 to the minus 9 divided by 3 squared. of 10 newtons per coulomb. So this is 10, this is 10. Now, if I think about how that vector breaks down, I'm going to have two components that are in this direction, and then two components in this direction. These are going to cancel out because they're equal but opposite. So I need to figure out what these components are and then double it, and then that'll be my electric field. The electric field of a single one of these is going to be 10, or not the y component. It is the y component, but I'm going to call it the I'm going to call it the x component because it's sort of on the side. But I'm looking at the adjacent to this angle. 10 cosine of 60, which is equal to 5 newtons per coulomb, and then I double that will give me 10 newtons per coulomb because I have 1, 5, and 1, 5. I'll remind y'all about this in the help session, that when you have an adjacent side, an adjacent component, that you use the cosine. Usually we use the cosine for the x component, but in this case it's the adjacent component, which is the relevant part. Let's see, what is the magnitude of the force on the 5 coulomb charge? Hold on just a second. Okay, I might remove this. So let's see. So F is equal to Q times E. I thought I had removed it. So we might have a different problem that's fitted in right here. 5 times 10 is 50 newtons. You're sitting at a certain distance from a point, you measure an electric field, you double your charge, and your distance is halved. So E equals KQ over R squared. I double my charge, I halve my distance. This becomes 1/4, but it's in the denominator, so I have multiplied my electric field by 8. Where does the electric field have the biggest magnitude? Remember, the electric field is given by the density of the E field lines, but here the E field lines are all the same. So E is the right answer. What is the sign of the charge on the right-hand plate? Well, electric field lines run from positive to negative, so it is negative. A person touches a Van de Graaff generator and their hair stands on end. Why? They have an excess of negative charge on their body. Yeah, that sounds right. Let's look at the other options. Electrons on their body have all moved to their hair. No. In fact, you get a bunch of electrons in your hair, but you actually have electrons all over your body. It's just they're all over. So all the excess protons have moved to the person's lower body. Protons don't really move around very easily. You can move a proton, but it's quite difficult, so that's not right. And they have excess positive charge on their body. Nope. It's they have an excess of negative charge on their body. And it's electric insulator. Electrons don't flow easily through it. Neutral metal ball. Boy, we've had several of these. There's a rearrangement of electrons in the ball, which is not allowed charge. Okay, well, the fundamental unit is 1.6 times 10 to the minus 19. So this would be like 1 proton plus a little bit extra. Who's my favorite person? I'll let y'all guess, but it's not any of these three. Although I'm glad that those people work hard for our nation. But my favorite person is my wife. Okay, that's the end. Again, there might be one small change in this.